Hello, my name is Tigmanshu Bhatnagar, and in this presentation, I'll be demonstrating how we transformed a monolithic sheet of Nitinol into a passive, reconfigurable, tactile pixel array at real resolution. I'll be presenting this work on behalf of Nikolai Marquardt, Mark Medovnik, and Catherine Holloway. We are all from the University College London. A proof of concept prototype that we call Tacilia contains 729 independently addressable tactile pixels made from just a single sheet of Nitinol. The working principle of Tacilia is based on the shape memory effect, which allows us to compress these pixels to their flat configuration in the martensitic form or in the cool form of the sheet. However, they actuate or bend out of the plane as soon as they are heated. We first laser cut cantilever U-shaped beam pixels on the sheet. These pixels have been designed so that the maximum strain on bending remains below the maximum recoverable strain of the material. To train the pixels, we follow the procedure for one-way shape memory training, which has been extensively documented in existing literature. Now, this trains the material to remember its new austenitic form or the new bent form of the pixels, so that they actuate as soon as they are heated. However, they are quite stiff and do not go back to their flat state. To overcome this challenge, we anneal the material and we get the mechanical reconfiguration that we wanted. However, as soon as the pixels are heated up again, they snap back to their actuated state and retain their position until they are mechanically forced back. If we see the parameters, then we achieve a maximum out of plane displacement of 0.4 millimeters with a peak block force of 0.28 kilograms. The block force when the sheet is at room temperature is 0.23 kg, and the peak temperature to achieve the peak block force is 49 degrees Celsius. However, to reconfigure is 38 degrees Celsius, and the rate of cooling is 3.61 degrees Celsius per second. In order to evaluate Tacilia as a tactile display, we first evaluate the absolute threshold of scale for simple shapes. We compare fill squares to outline squares and find that people have a greater confidence in recognizing shapes through their outlines, which improves as the scale of the shape increases. In the second study, we understand how people discriminate between simple tactile shapes of a square, triangle, and a circle. We find that they are able to accurately determine these shapes 82% times of this display. Finally, we invited them to interact with Tacilia using a hot air jet pencil to manually draw freehand sketches directly on the sheet. People were able to develop their own unique ways to gain tactile feedback from the interface. Erasing, however, was considered to be fairly easy, and with a slight bit of manual force, people were able to easily erase whatever has been drawn. So in this work, we presented a method in which we can transform a single sheet of Nitinol into a passive tactile display. We achieve a block force of 0.28 kg and 0.4 millimeter displacement, which is sufficient for tactile reading directly on the sheet. And we also demonstrated its use for new interfaces to read tactile information, draw tactile information that can be easily erased as well. We invite you to read the paper for more details about this work and invite you also to the demonstration that will happen later in this conference. Thank you.